Okay, today we start a new section. This section is very brief. I only take 2 lectures today and Friday. We focus on understanding the parameters we need to model the transmission lines, especially on the high voltage power lines. But definitely similar approach also apply to diffusion lines at lower voltage. Okay, so as introductions, transmission lines have 2 types. The first one is called overhead lines. You can see those lines everywhere. And the second is underground cables. You may not recognize where those cables are. And usually they stay in the areas, definitely for the diffusion lines, and there may be a more underground cable. I take probably maybe up to 20%, but at the high voltage level, so usually transmission lines are overhead lines, not underground cable. But in some areas like a rich area, the people don't want to see the overhead lines, so they prefer to pay more to put the lines underground. So that can happen. So at the end of this section, we'll explain what the difference between the overhead lines and underground cables. Even they can model by the same set of parameters, but in general, underground cables will have more capacitance than overhead lines. So that can be some problem, which means if you are operating a system with completely overhead lines, so under the highly loaded condition, the low voltage could be a concern. But if you operate a system with completely underground cable, the high voltage can be a concern. So they have different strategies. So we'll explain that one at the end of this session based on one example. So for high voltage transmission lines, underground cable only take no more than 1%. In terms of the voltage level, so here we talk about transmission lines, but we include sub-transmission system lines into this category. So which means we study the voltage typically above 69 kV. So usually 69 kV is still at the boundary between the transmission and the sub-transmission. But about 115 kV, so that voltage level is considered transmission voltage level. And even like 161 is still at the boundary between transmission and sub-transmission. But above 230 kV, so 345, 500, and even 765, so they are at a very high voltage level. So they are typically the transmission system power lines. So there are a number of properties we need to model for each transmission line. The first one definitely is a series resistance, because unless you use superconductor in the ambient temperature, you can get rid of the resistance. But realistic, you also always need to consider resistance. Definitely, you can make conductor to be very large, and that can reduce the resistance. But we can still model. We still need to model resistance for most of the cases. You need accurate calculations. For very high voltage lines, because the size of conductor, the resistance can be ignored if you focus is not on the loss of the line. The reason to cause the series resistance is mainly because of there are a lot of conductor. So from outside, you just see a single line, but inside there the composite of designs, which are called stranding. And also another is the skin effect, because when you operate the line in the AC power system, the current will be alternating all the time. So that the skin effect also increase the resistance. So we'll go to that in more detail. The next parameter is a shunt conductor, shunt conductance. So conductance is basically another way to call resistance, but because it is connected not in series with the line, but in the shunt, a parallel connection with the line. So we call it shunt conductance. So conductance is just a reciprocal of a resistance. Shunt conductance is another connection between the line to the ground, not to the other end of the line. definitely you only have any direct connection between any line to the ground, right? That's called short circuiting. But because you operate the line at a very high voltage, that can make part of the air surrounding the insulator conductor to conduct current, which means you can lose energy because you operate this very high voltage line. So one picture shown here is called corona effect. So that is the picture taken on the very high voltage insulator. So you see those lights that indicate it's actually losing energy because of part of the air surrounding the conducting insulator conducting current. So actually you are losing some electricity when you operate this high voltage line. So that is called the ionization of the air. That effect usually can be ignored. Basically, in the next session, when we go into the model of transmission line, usually we ignore shunt conductance. The third one is a series inductance. Series inductance is basically just because of the magnetic and electric field of the transmission lines with alternating current. So there will be a magnetic field induced, which can delay the current phase compared to the phase of the voltage. That can be modeled by some inductance. Definitely, we also need to model shunt capacitance. Shunt capacitance just model the charging and discharging of the electricity of the conductor. That will create something similar to a capacitor. We'll model all the four properties. Okay, so I list the three formulas. That's the only thing, only takeaways for this section. So if you already understand completely those three formulas, you're done. This section is that's only knowledge you need to take away at the end of Friday's lectures. So the remaining slides focus on explaining each of the formula and try to prove those formulas. So first formula can be very simple. Most of people already know this one, right? So if we consider the conductor, the resistance in DC circuit is proportional to the rho. Rho just define the material, the resistance nature of the material, and L is length. A is the size of the conductor, area of the conductor. And so in AC circuit, we only just need to know the AC resistance is slightly higher than DC resistance. How much higher? Just about a couple of percentage, like 2%, less than 2%. If you operate the conductor in the 60 Hertz system. And inductance is basically just calculated by this formula. So you see it has two parameters. GMD is called the geometric mean distance. GMR is a geometric mean radius. Okay. So if the transmission line has just single conductor, so the GMR will be physical radius, and the GMD will be the physical distance between the conductor. But if you have a more complex design, so we need to figure out a way how to estimate the GMD and GMR. Capacitance also depend on the GMD and GMR, but capacitance GMR is slightly different. The difference lies in the fundamental difference between the electric field and magnetic field. Okay, so if the electric field and magnetic field are completely symmetric or become analogy to the other, equivalent, so there will be no difference between the GMR for calculating inductance and GMR for calculating capacitance. Yet we'll go into that detail later, but does anyone know the fundamental difference between the electric field and magnetic field? Or what makes theirs different? Okay. So in the equation, they can be analogy to each other, right? It can be a counterpart to each other, but they have an essential difference in physics. Okay, so magnetic field can be anywhere, but electric field can be only outside of the conductor. Okay, that's one reason making those two radius are different. So if you're able to design some material having no magnetic field inside of the material. We still use this formula, but that formula will basically take this GMR, not that one. Okay, that's the only difference. So we'll go into that later. Okay, so basically GMR or GMD is just a geometric mean distance or radius of the conductor. Because conductor is not just single piece of metal, right? So let's say if this is the shape of some conducting material, it's not completely symmetric. And in the calculation, we want to find the geometric shape with better symmetry. So we use this way to calculate the average distance, right? So dimension. So they have the same volume, but the dimension is completely symmetric. So that's the formula we're going to use to calculate the GMR and the GMD. All right. Later we'll show the GMRC is bigger than the GMR for calculating the inductance. Okay. So those two pictures are overhead transmission lines, and you can tell the towers. You can easily see. Okay, so for this tower, you have three sets of insulator, so it carry basically 3 transmission lines. And for this, the left tower, you have a 6 insulator, so it's actually carry 2 sets of transmission lines, and each set has 3 faces. But if you count how many lines, wires in the first picture, so you see maybe 1, 2, 3, 4, 5, 6, but on the top, you also see a few wires. So the top one, not transmission line. The top wires are called the shelled wires. So they are not delivering electricity over the conductor. They try to provide a circuit for if you have any fault. It will just help to protect the transmission line locally. So it just give you some if there's any grounding fault, so that shelled wire will be functioning. But in most of condition, you only have those 3 transmission lines. So you can recognize which is the shelled wire, which is transmission line by identifying the insulators. And the size of insulator tell the voltage of the lines. Okay. Regarding materials, basically most of conductors are made in aluminum because they have a relative low cost but high strength to weight ratio than copper. In the past, you can there might be some line in copper, but not most of in aluminum. But you can add some material to help reinforce the line. So for example, this design. So if you see those 4 letters ECE421, that stands for aluminum conductor steel reinforced. And if you see ACCC, so that's called aluminum conductor composite core. So for the first one, the inside they have a steel, try to give a better strength of the entire transmission line. But the second will have composite core, which is not conducting material, to give you help to improve the strength of the line. So here, just give you the picture of the two. So the left is just the EECS, and right is ACCC. And this picture is ECS. So the inside, you see there's some steel just to make the transmission lines stronger. So later, we may study how to calculate the GMR or GMD for this design. And there's a number of examples. We start from similar cases to more complex cases. We start from maybe 2 conductor, and then finally we make it more complex. Okay, so this picture, you see many circles. Each circle means 1 strand. Strand means it can be considered a single piece of conducting material, but they're closely contacting each other. Okay, so the entire one will become a treated as single conductor of a line. It can be considered 1 phase of transmission line. But when you look at the even higher voltage line, so even in this picture, if you look more closely, so in each phase, there's not just single straight line, there are multiple ones. That's because this design. So when you operate at even higher voltage, you can either make a very large size of conductor that will have more corner effect. So you have more shunt conductance, or you can split the conductor into maybe 4 smaller conductor, but you have short circuit connection between all the 4. So they still treat it as single phase of line, but that give you more efficiency for the electricity. So if you see such a 4 conductor bundle, so that usually for 345 to 500 kV, for 230 kV, you may only see 2 conductor becoming a bundle. So those are the what we can see about overhigh transmission line. So next we talk about the line resistance. So we can consider a solid round shaped conductor at certain temperature. Okay, so if you give it some direct current, so direct current will uniformly distributed among the conductor. So if the total current is I, so the density of current everywhere will be same. Okay, so that's then we can you can measure the resistance. So we call that DC resistance. DC resistance is just based on this formula. The rho is conductor resistivity. L is the size length of the conductor. So the longer the line, the bigger the resistance. And A is the cross-sectional area, which is basically this area. But when we come to a alternating current system, the resistance will be very similar, but will be slightly higher. The reason is when the current is alternating, okay, so current will generate a magnetic field indicated by H. H is just the intensity of the magnetic field. And the magnetic field H is also alternating, so that will create the eddy current. So you have a lot of eddy current everywhere inside of the conductor. And eddy current inside of the conductor tend to cancel each other. Because if you have one eddy current, you will have another eddy current this way. So actually, those 2 arrows are just pointing to different directions. Finally, they are canceled. So inside of the eddy current, that one can be smaller. So if you have more eddy current inside of the conductor, they will cancel each other. But on the skin, the eddy current are harder to be canceled. So that will make the current near the skin to be higher than the current in the center of the conductor. Okay, how much higher? So eventually, if we operate at 60 Hertz in the AC power system, so the average resistance of the conductor can be 2% higher than the DC resistance. Okay, so to calculate the resistance, if you need a very accurate calculation, you can first measure the DC resistance. Then based on the frequency, you can tell how much you need to correct or adjust the value. Maybe you need to increase by 2% if the frequency is at 60 Hertz. But typically you can use just DC resistance if you don't need very high accuracy calculation. The next one is about temperature. So if you already know the resistance measured at temperature 1, and you want to calculate resistance at temperature 2, so you just need to use this formula by giving the temperature 2. So it will satisfy a linear relationship to change the resistance. The higher the temperature, the higher the resistance. Okay, for aluminum, that the capital T here is 228 degrees. So that determines for material how easily that can become a superconductor. So this slide is the only thing we need to know about the resistance. So it's done. Okay. So when we just need to know this formula to calculate resistance and 2% higher if it's operated in AC circuit. All right. So next, let's move to inductance. So to talk about inductance, we have to quickly go over some concept from the magnetic field. So if I have a single wire carrying current I, and if you measure a circular path of the total length is L surrounding this wire, and you measure the magnetic field strength, okay, which is H. Based on the Ampere's law, you can calculate H. Okay, so there will be a magnetic field induced surrounding a current I. If we're able to count how many the density of flux along that circular path for a very small area, so you will see that there's a flux direction, right, pointing to the north in that local area. If you can measure the density of the magnetic flux, okay, so you can count the flux divided by that area, so that will give you B. B is called a magnetic flux density. So H and B are different things. H only depend on the current. H tell how much current, only depend on current and the distance to the current. Okay, it tell the how strong this field is, magnetic field is, but flux density depend on the material. So at that place, if that's in air, non-magnetic material, so the flux can be small. But if you put a magnetic material at that place, that can suddenly increase the density of flux. Okay, so if we know what the material is, so there will be only a ratio we call the mu zero. The B is proportional to H. There's a linear relationship. But if you put a magnetic material at that place, it will suddenly just increase B with same H. So you can make this lobe to be very high. All right, so this is what you have learned from 325 or from other courses, right? Does that sound familiar to you? All right, so we'll need to assume we know those facts. Then we can try to develop the formula for inductance of a single conductor, because we are going to utilize everything here, those pre-knowledge. So now we are ready to consider a single conductor, which has, a cylinder. We can treat it as cylinder, so with a center here, and this is the radius R, and the total current is I. But because we want to study the flux inside and outside conductor everywhere, so we have to make sure we have the formula describing the flux and the flux linkage for any distance to the center. So for instance, we consider this circle at distance of x to the center. And at that point, there will be magnetic field strength. We call it X. That only depend on current. It doesn't depend on material of this conductor, right? Because if you remember, we talk about there's some conductor. Outside it can be aluminum, and inside can be steel or different material. But for this H doesn't depend on any material at all. Only depend on the current and also the distance to the center. Okay, so Ix is actually now the entire current, and only part of the current. So if you think about if we treat it almost like evenly distributed density of current, so the area in this circle will determine this X, right? So the total current is I. So if we divide the circular area by the total area, that will be the X divided by I. Okay, so now we only consider part of this current. We call it X. Hx is just the magnetic field at the distance of X to the center. And the mu zero, we mentioned that is the ratio of the B to H. The meaning in physics is called permeability of free space or non-magnetic material. So for non-magnetic material, you can use mu zero. So if you know H, you will know B. But for magnetic material, the mu will be very large, much bigger. For this mu, this number is 4 pi times 10 to the -7. Okay, so you may wonder, this number sounds very interesting. It's not a rounded error, right? There's no rounding error at all. It's just called 4 pi because this value is defined. We'll explain this one in next session why this value is defined. Does everybody know this mu0 is defined value? Not a measured value, it's defined value. Yeah, we'll come back to this one in the next session. Okay, so now we're ready to calculate the magnetic flux density Bx. This is proportional to Hs, right, by a factor of mu0. But first, we need to apply Ampere's law to calculate. Ampere's law tell, so the current will depend on the magnetic field. Okay, and we just integrate if we integrate the magnetic field over a circle, and that will tell you how much current inside this magnetic field. So if you do this integration, it's very simple because we assume Hs to be constant. So we just do an integration over this entire circle. So that will be the 2 pi x. Okay, so we have this simple formula we can use. From this formula, the bigger the distance to the center, the smaller h we're going to have. Okay, so which means if s is go up and hs will go down, and the bs will also go down, right? That makes sense. That's similar to our feeling about the magnetic field. So we'll have this one to calculate the bx. All right. So next one, we need to figure out the flux linkage. Flux linkage is just the flux multiplied by number of turns. So in this course we use phi to mean the flux, and flux is just equal to the flux density multiplied by the area. The area is for the entire conductor, that area is A. But for smaller piece of conductor, you can calculate that part of A. So N here is just the number of turns. Okay, so if you have a wire connect, maybe there are many turns of the wires coupled with the current, and you just count how many turns. It's similar to the transformer. On each leg, you have many turns of the wires. You just count N1 by N2 will be equal to V1 by V2, right? That's the formula we use. So here, if you count, there's many turns of such wire you carrying the same current coupled with this magnetic field. So that number of turns is N. So we count how many turns multiplied by phi. So that will be called the flux linkage. The more turns, the bigger the linkage using the same flux. So the inductance of a non-magnetic material will be simply defined as the flux linkage divided by current. Okay, that's the definition of inductance. For this conductor, because we know the magnetic field inside, outside can be different. So we calculate the inductance separately. So we assume that the inductance will be the sum of two pieces. The first one is only caused by the flux linkage inside conductor. The second is outside conductor. So we're going to calculate internal inductance and external inductance. So the total will be the total inductance of the line. For the external inductance, when we consider current, we need to know the current won't change with the distance to the center, because inside, if you increase x, that current circulated by that by the circle of distance x will to the center of x will increase. But once it becomes outside, so this current will be constant, because once you go outside of conductor, the current won't increase anymore. All right. So next we use one slide to explain how to identify the internal and the external flux linkages and then finding the inductances. So the approach will be same. So first we need to find the flux linkage inside of a conductor and also the flux linkage outside conductor. Then we integrate the flux linkage. We calculate total flux linkage. Then from the total flux linkage divided by current, that will be the inductance. So similarly, we'll do the same thing. Okay. And this is still the same picture. We consider two scenarios. I use the red color indicate everything inside of conductor, the green indicate outside. So for inside, we're going to study the total inductance for this entire volume. But for outside, we have to define two distances. So one is D1. D1 is closer to the center. D2 is further from the center. And for both inside, outside, and we're going to start with a rectangular small area. So this one. So we have a length of 1. We consider the conductor has length of 1 meter, and the width is just a dx. It's just a division, increase of the x. And similarly, outside we also have the length of 1, and this dimension will be just d1 by d2. D2 minus d1. Okay. And we also we ignore skin effect here. So we just assume the current density will be evenly distributed among the conductor. Okay. So which means if we study a current for the total current for a cross-sectional area at distance to the center of x, so with increase of the x, so that current will increase because the total area increase. So total current will be equal to the density of current multiplied by the area. Okay, the area has the radius of x. But once the distance become bigger than r, which will be any area outside of the conductor, so current only increase anymore. It will be the total current I. So for that flux of that small rectangular area, that will be equal to the flux density multiplied by the area. Area will of that rectangular basically just ds times 1, because we consider 1 unit of the conductor. And the flux linkage, we need to figure out how many n we need to use here. That n just means how many times the same current is linking the flux for the d phi x. Okay, so we're ready to derive the formulas for each side. We start from the internal inductor. So the flux density is Bx, right? This is from the previous slide. And Hs is from what we proved from Ampere's law from previous slides. And for this Is, we need to plug in this one here. So we do some simplification. We'll get this formula. So the flux density is a proportional change, proportionally change with the distance of x. Okay, linearly increase with x. Next, we want to calculate the flux linkage. We call it the differential flux linkage because it's a flux linkage depend on the d phi x only for that small rectangular area. Why I call differential? Because the n is smaller than 1. Because the n only now the entire current is coupled with is linking the flux. Only the current inside of this circle is linking the flux for the flux linkage. So this n is less than 1. And only this portion of the flux is linked by the current. Okay. So next one, you just for this one, you just plug in this formula, right? And so you do simplification, and you can prove this flux linkage, differential flux linkage is depend on the S cubed and also ds. So this one will be integrated to calculate total flux linkage. So in the integration, you move those are all constant. Okay, so only just integrate this S cube. So if you do the integration, so this will be the total flux linkage inside the conductor. All right, so this result doesn't depend on the dimension of the conductor at all. So if you divide this one by the total current, this will be the inductance due to the internal flux. So this one has no dimension. It does not depend on the size of the conductor. All right, for the external, we start from the flux density. It's still the same formula, but here this I has become the completely I, because we go outside of conductor. So total current will be I, no matter how far away from the conductor. Does everyone follow? Okay, not many. Yeah, but yeah, it takes some time, so you can I show as much detail as possible here. So if you read the textbook, there's more tests to explain step by step. So for this flux linkage, and once you go outside the conductor, so the entire current is linked, is linking the flux, so which means the N is 1. So this entire conductor is a carrying current I, right? So if you consider any path surrounding this I, that number of turn is 1. So this is 1. But when you go inside, you still only just linking just a single current, not by many times, but that single current is a part of total current. That's why for the internal case, that N is not 1, it's less than 1. Does everyone follow this? That's the only difference between the two sides, right? Let me explain this one again. So think about transformer. So this is current I, right? There's a N is equal to 3. So if the inside of the this leg is phi, so flux linkage is basically just 3 phi. Is this clear? So phi means how many flux you have inside of this leg and a conductor. So and this is where it has 3 turns, which means this current is coupled with this phi 3 times. So flux linkage evaluate the linkage between the current and the flux. So there would be 3 times phi. Okay, so in our case, we have just a single line, which is similar to there's just single current. There's no many turns, right? We only just study the conductor as a cylinder. So only coupled if there's any magnetic field, phi. So the psi flux linkage is just exactly phi, because it's equal to phi multiplied by 1. And only just have a N is equal to 1. This is the case for external. So for external, we just treat the psi to be the same as phi. So they're basically the same, because only the current is coupled with phi only by once. But inside, that's very tricky. inside, which means so inside we have to go to the inside of this conductor. So this is total current I. But the flux is not outside the conductor, it's actually inside the conductor. This is phi. But because we study a circular path, and that circular path will only include part of I, not completely I. So n is not even 1, n is less than 1. Okay, so flux linkage is equal to the ratio, this ratio is less than 1. How much less? Is like S squared divided by R squared, because R squared is this area, This smaller area is pi S squared. So only this part of current is coupled with phi. Okay, so flux linkage can be lower than flux. This is different from a transformer. All right, we just move on. So we only just change n to be 1 for the second case. So we just move on and we get this formula. We still get this one to be integrated. And we're going to integrate from D1 to D2. So that tells you the inductance outside of the conductor only for the flux at distance from D1 to D2. That one does depend on the dimension, the distance to the conductor. So the external inductance depends on both D1 and D2. So if you increase D2, okay, so if D1 is the same, but your D2 is increased, you will make this rectangle area bigger. You will include more flux, so the inductance will increase. Okay, so what is the smallest value of a D1? The D1 will be here, right, at R. So which means D1 is always bigger or equal to R. And the D2 can go to infinity. But actually, in practice, it will never be infinite because this conductor only just means the part of this circuit. To make it a circuit, it has to go back somewhere. If you consider a single phase AC system, you have this conductor sending current to this direction, and at a certain distance, you have to send the current back to the source, to the equipment. So that distance will be the largest distance you can have for D2. Okay, D1 will be will be bigger than R, and D2 will be smaller than the distance between two conductors. All right, so we need everything for calculating the inductance for single transmission line now. So we will start from those two formulas. The first one tells the total inductance inside the conductor. The second tells the inductance due to the flux linkage outside conductor as two distances. So we consider a transmission line to make a single circuit. So we have the current maybe sending this direction and opposite. Yeah, current sending this direction and come back to the other direction. So finally, you can imagine this can make a circuit. On one side, there's a source. The other side, there will be load. This is what it means. So we only just study one section of this this conductor. We just cut the two conductors at the same dimension, and we assume the distance is d, and each side of the conductor may have different radiuses. So let's study the inductance of the first conductor. So from the formula, we need to add first internal inductance and external inductance. For internal inductance, that will be this one. External inductance, so D1 need to be R1. So we calculate starting from the skin of the conductor. The D2 will be the distance between the two conductors, because we cannot go beyond this conductor. The magnetic field will be stopped somewhere at the second conductor. So that will be the total inductance for the first conductor. Okay. And so next we notice, those 10 to the -7 are the same. So we try to merge them to a simpler formula. And we change this one, the half, to a 2 times a quarter. Then we change this a quarter to a log e to the power of a quarter. So then this one will become, then we can move this one together with the second item. We'll create this formula. All right, so we further simplify. There will be this item. So if you compare, this is the total inductance. You compare this formula to the formula only for the external inductance. They have almost same form. The only difference is this denominator. It's a little bit more complex. So we just simply define this denominator as ds. Okay, because it only just a factor multiplying the radius of the conductor. So if you calculate the e to the power negative a quarter, so that is equal to 0.78 around this value. It's slightly lower than 1. So we call this one to be a ds. So by defining this one, we can largely simplify the formula of inductance and further assume the two conductors are the same. They have the same radius. That can help us further simplify the formula. So okay, so you have two identical conductor that make a single circuit. One sending current sending a current coming out of the screen, and the other sending current going to the screen. So that inductance of each conductor will be this formula. Okay, so you see this formula is basically has the same form of the formula for external inductance. And depending on what unit you use, if you use Henry per meter or millihenry per kilometer, so you can choose between the two formulas. So this has the same structure of external inductance. So ds here is called GMR for a single conductor. It is equal to the radius of a fictitious conductor having the same inductance as the actual conductor, but no internal flux. We know that's not possible, okay, based on the physics of this universe. So you cannot have the zero flux inside of the conductor, but it just assume you can make such material inside the material. There's no flux, no magnetic flux at all, okay. And that material to generate the same inductance will have this radius will be 78% of the actual radius. That's what they mean. All right, yeah, I have a, yeah, let's continue talking about this one on Friday, right? So Friday we'll talk about how to utilize the formula from previous slide to study the inductance for more complex design.